Okay, so in this video, we're simply going to talk about linear momentum and collision, and we're going to start by looking at some few formulas that are needed for you to be able to understand the way that questions are going to be phrased under linear momentum. So the first thing that we're going to discuss is what momentum is. So momentum is just the product of mass and velocity. So momentum P, mass times velocity, that is momentum. Momentum can only exist if something is moving or if something is in motion. So meaning everything that has momentum also they have kinetic energy. That's what we have. Now, depending on whether you have initial momentum or final momentum. So initial momentum is why you use initial velocity. So we're using U, I'll use U there. Then final momentum is why you use final velocity. Let me show it by saying we're using a V. And like I said, momentum can only exist if something is moving. So a car that's parked cannot obviously bash you, right? Because it has no momentum. Yeah, and momentum is directly proportional to the mass and the velocity. So increase in mass will increase the what? The momentum. Increase in velocity will also increase the what? The momentum. And we're just going to say momentum results into collision, or it causes collisions, and we have two types of collisions. There are three in the actual sense, but the common ones are simply two. There is elastic collision and there is inelastic collision. So elastic collision is when the particular objects that are colliding become independent after the collision. So they are independent after the collision has happened. Then here in elastic, they get attached. They start to move together after the collision has happened. So we're going to discuss the formula that is needed under elastic in one dimension and also in two dimensions. And under an elastic, there's only one formula which is in one dimension when they get attached. Yeah, so either way, we're just saying there's still going to be here. There's going to be conservation of energy because the objects are simply conservation of energy under elastic, because the particles are still going to move independently afterwards. They just share the speed that they have. So we're just saying in elastic, so I'll start with elastic. This is in one dimension. So elastic collision is just as saying there is, let's say, object A and object B, right? This has mass. Let's call this mass 1. Let's call this mass 2. This has initial velocity u1. This is u2. Then we're saying these guys collide. This is before the collision has happened, right? This is in one dimension. Let me just say 1D. Then after the collision has occurred, so they bump into each other. Let's say you have this guy coming this side and you have this guy at rest. It could either be at rest or also be moving. So then they hit into each other. Then they move separately. They move either in the same direction but separately, or in opposite directions but still separately. This is after the collision has occurred. A, which is having mass 1, the mass is going to be intact with a new velocity. Let's call it V2. Then object B with its mass and the velocity V2. So we're saying if this is elastic, meaning they're independent, the momentum, the initial momentum of A, which is mass 1 times U1, plus the initial momentum of object B, which is M2 and U2, is equal to the mass 1 and V1 plus mass 2 and V2. So this is the equation that we use if we're having elastic collision in one dimension. So how do you know it's one dimension? There won't be any angles that will be specified. They won't mention any angles. So they will say this thing is moving in the horizontal. But you have to be careful because velocity can either be positive or negative, depending on where your object is going. So if it's going like this, velocity, whether initial or final, has to be taken to be negative because we're going in the negative direction of our x-axis. Then if it's going like this, it has to be positive. So generally, we're saying this is the formula that we use if we're dealing with an elastic problem in one dimension. This is what we have. Hope this is okay. And this also means that there is conservation of energy. The kinetic energy of the first object, the initial kinetic energy, plus the initial kinetic energy of the second object these guys here are equal to the finals as well. The final kinetic energy of the first object and the final kinetic energy of the second object. So this is the conservation of kinetic energy that we have. So this equation is very important. Then how about in 2 dimensions? So I'll finish elastic in 2 dimensions before we go to inelastic. So elastic now in 2D. So in 2 dimensions, we're just saying it's always going to be a case where one thing is moving, the other one is at rest, mostly. So let's call this M1, let's call this M2. This is object A, this is object B. So if these guys are moving, this is also called glancing collision. This is in 2 dimensions. So let's say this is moving with initial velocity 1, u1. This is at rest, meaning it has u2, which is 0 if it's at rest, or if it's given, you use whatever is given. Then once m1 glances at m2, let's say m1 goes in this direction and m2 goes in the other direction. We have something like this. So it's in 2D because of the angles that we are having. This here is going to be m1. Object A has gone down, then object B has gone up with an initial velocity here v2. This has initial velocity v1 because this here is what? m2. So this is how you know it's in 2 dimensions, when there are angles after the collision has occurred, meaning they have gone in at particular angles with respect to the x-axis. So we are supposed to resolve each velocity on the before part, on the after part. This is before, this is after. So we resolve this into an x component, which is v cos alpha, phi. To just distinguish these, I'm using phi and theta here. Then there's going to be a y component, which is just going to be v1. This is going to be v1, then sine phi. Then same applies for m2. We're going to have the y component, which is v2 sine theta. Then we have v2, then cos theta. So meaning we need to have momentum in the x and momentum in the y. So we're going to create momentum in the x and also an equation of momentum in the what? In the y-axis. Because momentum depends on velocity, and velocity is a scalar. So meaning whenever you multiply a scalar, which is mass, and a vector, which is velocity, the answer is going to be a vector, which is momentum in this case. So we're going to create the first equation in the x-axis, which is m1, because these guys are moving in the x. So it's going to be m1, then u1 plus m2 and u2. This is mostly 0 because it's always at rest. Then the x component of m1 is this guy here. So we'll say m1 times the x component velocity of m1 plus we say m2 and the x component of the velocity, which is v2, then cos theta. Then here in the y, this is not jumping up and down. Even this is not jumping up and down. So this is 0 plus 0 is equal to the y component of our m1 is facing down. This velocity is pointing down. So we'll say negative m1 multiplying v1, then sine phi, then plus this other guy here, m2, is pointing up. So that's v2, then sine your theta. This is basically what we have. So these are the 2 equations that we use whenever it's in 2 dimensions and it's elastic. Then if it's inelastic simply means one object gets attached, or they get embedded, they start moving together. This is only going to be in 1 dimension. This is just saying object 1 with its momentum, object 2 and its momentum, initial momentum. This is before. After the collision, these guys are moving with the same, they are attached. So we'll add them like this. We'll treat them as if it's one thing. They're moving with the same velocity. That's basically what you have. So this is before and after. So that's the difference between elastic collision and inelastic collision. So this is how you can differentiate them. Now let's look at our problem here. The problem here, they are saying a 5 kg steel ball strikes a wall with a speed of 10 meters per second at an angle of 60. That's what they are saying. With the wall surface, the ball bounces off with the same speed. So the same speed, which is 10 meters per second. and is in contact with the wall for 0.01 seconds. That's what you have. So here, maybe let me add one more thing. Since recall, you learned that force is equal to mass and acceleration, right? And here we're simply saying momentum is mass and velocity. Remember what acceleration is. Acceleration is final velocity minus initial velocity divided by time. So meaning I can just cross multiply here with a t and just say at, or rather here I can just replace, to lessen the burden here, I'll just say F is equal to m. Where there is acceleration here, I can put v u over t. You can have that F. So m will multiply everything on top. That's mv minus mu. This is over what? Over time. So when you multiply force times time, you are getting Ft is equal to mv minus mu. Now remember what mv is. This is final momentum. Then initial momentum is mu, right? When you use initial velocity. So this part here is the same as us saying it's the change in momentum. Change in momentum just means final minus initial momentum. So we're just saying force times time is just the change in momentum, which is also going to be represented by letter I. I is simply force times time, which is now going to be called impulse. So impulse is just the product of force times time, or the change in momentum. That's basically the impulse. So here they're simply saying this is the time given. What is the change in the momentum of the ball? So you come here this side. So you look at your diagram. This is the diagram that you're having, right? There was velocity coming this side at an angle. So let me use a different color. Okay, so if you take it to be in this context that you're seeing here, so I've just rotated the page so that you're able to see that the velocity we are having is coming from this side. We have an angle of 60 there, then again it leaves this side. So this is like your initial this side. So you're having initial momentum, or rather initial velocity. I'll say u here. I'll call this u, I'll call this v this side. So we're going to have two components, right? Because we're going to resolve this. I can just turn this into an x or y plane. This is going to be the same as 60. Then I can alternate this to have, we can call this to be our x. That's going to be whatsoever our u is. Our u is going to be equal to, u cos 60. Then we're going to have negative u sine 60 down. The same applies here for this v. We're going to create v cos 60 and also the y component, which is v sine 60 there. So that's what you have. You have to resolve it like this so that we have our two x's. The x's are going to be v and u this side. So we're looking for, the question is asking for what is the change in momentum of the ball. So we're just saying initial momentum in terms of the x and also initial momentum in the y as well. That's what we need to do. Okay, so we have our initial velocity here. The easier way to do it is that our final velocity will still be the same this side. So here we're going to have the velocity has to be resolved in the x and the y. So you are going to get the final velocity in the final velocity here in the x. That's v. I'm going to use v. Is just going to be in the x-axis. That's v, which is 10. Still cos 60. Then the y component is simply going to be we are having vy, which is just going to be our 10, then sine 60 as well. So these are just the components of velocity. Then here in this quadrant here, we're just going to resolve this. So I made this point here to be my x-axis, my origin, so that I create something like this. Then we made this to be our angle, which is simply 60, so that we resolve this velocity here, the 10, into, so if I turn it like this, meaning this is going to be my x is going to be the u, so I'm going to use u because that's initial. The u in the x is just going to be equal to my 10, still my cos 60. Why cos? Because we're still using cos because it's in the fourth quadrant. According to this axis I've written here in blue. So in the fourth quadrant, cos is positive. Then the y component of this thing is going to be uy, which is just going to be negative 10, then sine 60, because sine is negative in the fourth quadrant. So now we are looking for momentum. The change in momentum in X and the change in momentum in Y. The question here is specifically asking for what is the change in momentum of the what? Of the ball, right? That's what we are having. So we have to get the change in momentum in X, the change in momentum in Y, then get the actual change, the resultant change. So here we're going to get momentum is mass. The mass here is given to be 5 kg. So we'll just say 5. Then we'll say the one in X is what? The one in X here, the final is that. The initial is just this. So we're just going to say 10, okay, cos 60 minus again a 10 cos 60. This gives us a 0. So hope this is okay. You get a 0. Then the change in Y, that's the only place where we can see significant change. That 5 multiplying, we're getting this guy, the final minus the initial. So that's 10, then sin 60, then minus negative 10, then sin 60. So now we're going to get 5. These are going to be the two of them. So 2 times 10, then sin 60. This will give you what? This is 10, that's 100. So the answer is 100 sin 60. That's the change in momentum in Y. This is basically what you get as your overall change in momentum. Because even if you try to get this, even if you try to get the change in momentum for X squared, then plus the change in momentum of Y squared, you still get this same value. Because the other one is 0, the X is 0, this is 200. Yeah, so you get 100 sin 60, which you can calculate. So because I don't have a calculator, you can just confirm it, get what is required. So that's the change. When they say the average force exerted on the ball by the wall, we just divide this, because we say, remember we said force is equal to change. Force times time is impulse, right? Impulse, which is change in time. So now the time was given. So what is the force? We have 100 sin 60. The time is 0.01. So this will give you the force, which is in newtons. Yeah, so this will give you your answer to number 2. And here they are simply saying state the law of conversion and list 3 characteristics of perfectly inelastic. So this is supposed to be conservation. Yeah, this is supposed to be conservation. So the 3 laws of conservation of kinetic. Okay, this here should help. So the conservation of momentum, we just say the total energy in a closed system is going to be the same. So the total momentum remains constant. So the momentum before and after the collision is always going to be the same. And the formula just says P initial is always going to be equal to P final. In short, we just say the change in momentum in something that obeys the rule has to be 0, because we're just saying the law says initial is equal to final. Meaning, if you take the initial this side, meaning the change in momentum in a normal closed system should actually be what? Be 0. This is basically what you have. It's like when a car bashes someone, or rather into a house, all the energy that the car had is going to be transferred to the house. Let's say this is our house. The reason why the house sustains damages, you see cracks and everything else, is because it's not designed to move, right? It's designed to just be still and be in position, but then it's trying to accommodate the energy that it's receiving from the car. So it demonstrates, or rather it protests through through it having cracks and it just being disfigured. So either way, that impact, the noise, all the energy that you're going to have in between that collision and after it's done, that impact is going to be preserved. So that's why we say it's what? It's simply conserved. Then when we talk about the 3 characteristics of, here they're saying, perfectly inelastic collision. So if this is actually true, there are these characteristics here. So this will be easy for you to just, we're just saying objects are going to stick together. There's maximum kinetic energy loss. Inelastic, we said, energy is only conserved when it's elastic. But if it's under inelastic, energy is not conserved, because these objects get to stick together, right? In order we have maximum energy loss. Though momentum is conserved, because all the energies that you're going to have, energy loss is equal to energy gained, because you know the law of energy, it can never be created nor destroyed, right? Then the same final velocity for the 2 objects, because they're coupled together, they're moving together at the same time. So those are the characteristics of perfectly inelastic collision. Then C, they are saying let M be mass of the gun and small letter m be the mass of the shot. Before firing, both are at rest. On firing, let V be the velocity of the shot and V be the velocity of the gun. Find V and explain your final answer. Then number D, they're saying define impulse and show that impulse equal to the change of momentum. So we've already done this. We've already shown this. If you remember, we defined impulse is the product of force and time, and we reached a stage where we showed that this here, the change in momentum is equal to impulse. Yeah, so you just have to recap on how we derived Ft. That's basically what they want, this whole process here, until we reach at this point. That's what they want. Now to answer the second part, this guy here, part C. Okay, so according to part C, they are looking for the velocity of the gun. That's what they want. So to not waste our time, I'll just show you here how we should get it. So we know there's going to be conservation of momentum, because these guys, it's going to be an inelastic case, inelastic, because they're going to be attached at the end, right? So that's what we have. So initially we're saying, let's start with here. They are saying to find the actual velocities of the shot and the gun after the shot is fired, we can use the principle of conservation of momentum. Before the shot is fired, the total momentum of the system is 0. So because there's no motion, right? So this is what you're having, because the final velocity is, there's no movement at the beginning. So you have the mass of the gun and its velocity. So we are going to have, okay, let me just show you this here. Okay, so here's the thing. They're simply saying we identify, we can choose the mass, you have this. So the first equation is given to be here, the conservation of momentum. Then we know to say if the gun, according to relative velocity shot with respect to the gun is going to move a bit backwards whenever a shot is taken or is fired. So that recoil velocity of the gun is given by the velocity here, the shot that you are getting. The Vs is equal to V, the velocity of the gun, plus the initial velocity. So the relative velocity is just going to be given in terms of U. We're going to use U as the relative velocity. This is the U you are seeing here. So the relative velocity is just the velocity between the gun and the shot that was taken. We always take the velocity of the shot minus the velocity of the gun. We can make the velocity of the gun to be, the shot to be the subject of the formula. So in the equation where momentum was conserved, we can now replace, wherever there's Vs, we can put U plus Vg. That's a replacement that we make here. This is what you're able to see there, wherever there was Vs. And we can now just operate it to just make V, the velocity of the gun, to be the subject of the formula. And when you're done, this is what you get to be the velocity of the gun. And you can replace this back into the velocity for the shot. You can also get the expression for the velocity of the shot in terms of the masses, which is the velocity of the shot. So you have the two expressions here, the velocity of the gun and the velocity of the shot. This is basically what was needed. This guy here for negative mass of the shot times the initial velocity, the relative velocity over the two masses added together. So this is what was needed. The question was a bit tricky, but yeah, this is what you had. So this summarizes linear momentum. Yeah.